Section 4.1 in Chapter 4 is called Generating an AC Voltage. As strange as it may seem, we actually begin the discussions of a DC generator by understanding how an AC generator functions. And what we're going to find out is that all generators basically operate the same way, but based on their construction, and particularly the DC generator has this thing that we'll just call it a thing called a commutator, which takes this AC voltage and converts it to a DC voltage simply by the way that the machine is constructed. So let's look at the detail of that, and starting with figure 4.1 in our text. So what we're looking at here, it's on page 72 in our textbook, is an elementary AC generator. And this is going to help us understand the way that the DC generator works. It shows, I'll just point out a few things. This part of the generator is actually a coil. And, so imagine that there are strands of wire that are formed in coils. And, that is this entire part of this, okay? That's a coil of copper wire. And so what we're saying when we're looking at this, and we're going to designate this as side A and this is side D. And what we have is a permanent magnet. Makes the explanation simpler. And we would think about the magnetic field going in this direction from north to south. So, what we're going to do is we're going to turn a coil through a magnetic field. Now we know a basic law principle of electricity is whenever you have a magnetic field and you turn a coil of wire in through that, you're going to induce a voltage across that coil. Okay, so that's what's going on here. All right, so let's put a few things here. Magnetic field, and then notice that the direction of rotation is given, and this is really just arbitrary, but we're going to say that it's turning counterclockwise here. Okay, so it's turning counterclockwise across there. All right, so that's what's going on. Now, what's interesting about this is that here's what differentiates this type of generator from other types of generator. And it's the way that we connect the coil to the load. So here is a wire, and it's going through this conductor here, and it's just a connection to the copper coil, and it's a larger piece of copper, and it rotates as the coil is turning, and something would cause this coil to turn. We could be turning it manually, or we could have it connected to a turbine, that's like a steam turbine or something that's causing this to rotate. So what happens is, as this coil rotates, these conductors are flush up against these slip rings here, and they turn inside of the slip rings. But notice that there is an electrical connection between this coil and this slip ring. So that's the way that we're able to transfer this generated voltage out of this thing. All right, so these things here, again, are called slip rings. And here's just the coil, and we have a way to physically touch those slip rings as this coil is rotating. Now, these are also a big part of what's going on, and these are called brushes. And we're going to designate one as an X and one as a Y, just for a frame of reference. And then what the brushes allow us to do is to actually have a physical connection to some type of load. Okay. Now this load could be a light, or it could be a motor, or it can be anything that we wanted to connect to this generator. All right. So there's the basics here. Rotating coil rotates through a magnetic field, generates a voltage. That voltage is transferred ultimately out to the load through the connection to the slip rings. These brushes physically rest against the slip rings, and then we have a way of connecting the brushes to the load at this point. All right, so that gets us started with this idea of how this thing works. All right, let's build on that. Now, there's a fundamental equation, and this is one that I just want you to plant in your brain and don't forget it. It actually comes from chapter 2. Now, the way that we're approaching chapter 2 is that as portions of chapter 2 come up in our discussions, we're going to revisit that as it comes up instead of taking it as a chapter by itself. So equation 2.25 shows this relationship between three things. And those three things are indicated in this figure 4.1. The first one is the magnetic field strength, and it's given, or flux density actually we'll call it, and it's given by this part that I originally, and should have kept doing that, shouldn't I? Originally outlined in red. And what that shows is this is the strength of the magnetic field. And I'm showing that magnetic field with the red lines. The L in the equation here is the length of the conductor that's exposed to the magnetic field. And then finally, the V is the velocity of the rotation. How fast is it turning? And that is given here. It tells us it's turning at 60 RPMs. Okay? And what that does is that quantifies the value of the voltage that would be generated out here that would be available to the load. If the magnetic field strengthens, the voltage goes up. If the length of the conductor that's exposed to the magnetic field increases, the voltage goes up. If the speed increases, the voltage goes up. So they're all proportional. And as they increase, the voltage goes up. If they decrease, the voltage would go down. So when we're looking at this figure, what we want to see at this particular point, if we could see these magnetic flux lines, we could picture that. So what we're seeing at this point is this coil, side A and side D, is at the point in rotation where it's cutting the maximum amount of magnetic flux. Okay, now if that coil were here, right, if it had rotated 90 degrees, there is no magnetic flux in those positions. But where it is right now, it's generating a maximum amount of voltage because it's cutting a maximum amount of flux lines. All right, and then we're going to see what that looks like on the output here when we look at graphing this voltage output through one complete rotation. So let's explore that a little bit here. And let me pause this and let's look at a different slide. So this is figure 4.2, and this would be the output of the voltage that we would see if we had an oscilloscope connected out here between this brush X and this brush Y. Okay, so this is figure 4.2 is showing what the output would look like if we had a way to, and there's a way, of course, an oscilloscope would do this. And so what we're seeing here, this is the voltage generated, and it says E sub XY. So that is the voltage between the brush X and the brush Y, okay? And then what he's saying at this particular point in this picture, right? This particular point, it's cutting the maximum amount of flux lines, so the voltage is going to be at its highest, and that's what we're seeing right here at this point, okay? Now, if we rotate this coil through 90 degrees to this point, let's go back and I'll show you. Think about this, and this has rotated through, and side D is here now, and side A is here. Then at that point, there's no magnetic flux lines being cut. So at that point, the voltage that's generated would be 0 at that point. If we rotate through another 90 degrees to 180 degrees, okay, so let's say now, let me get rid of this. If that were to occur, then now this would have rotated through till side, it didn't come out real well. Try something a little darker. So at that point, additional 90 degrees, side D would be there and side A would be there, okay? So it's rotated through, it was here and now it's here, and what that looks like is here, which is also a maximum voltage, but it has a negative sign in front of it, which tells us that the polarity has reversed, okay? And that has to do with the coil and the pole that it's crossing, and the direction of the current that flows through. But anyway, the polarity has changed. Now, if I rotate through to another 90 degrees, and we could see that now, that would put side D here and side A here. Again, we're at one of these 0 points in the voltage here, right? Would be another 0 point here. So that would be 0 voltage, which we're calling EAD, which is coming from the two side designations, side A and side D. And then we rotate again 90 degrees more, and we're back where we started, back to the positive 20 volts. Now the 20 volts, you know, that's just a number we're using here to make this demonstration. But what we're seeing are these positive maximums, negative maximums, crosses the 0 point twice, and this would be a full 0 to 360 degrees transition from here to here. And so, you know, basically what we've done there is we have, you know, created a sine wave. And he says for discussion in this, he says this is rotating at, remember where he said it's rotating 60 revolutions per minute? 60 revolutions, RPMs, revolutions per 1 minute would mean that it is making one turn in 1 second, right? Since there's 60 seconds in 1 minute, it's making 60 in 1 minute. It'd be making 1 revolution in 1 second. And we even, you know, we even should know too that the frequency is described as the number of revolutions per second. So this would have a frequency of 1 hertz at that particular point. Okay, so he shows us another view of this, where with this slide, we're looking at angles of rotation. We can also equate the same rotation in terms of time, which we're going to find is usually more beneficial to us. So here is 1 second. So in 1 second, we go 1 complete cycle. That gives us 1 hertz. And we're going to have the 2 positive peaks. We're going to cross 0 twice. at half a second, where at this point, at a quarter of a second here, 3/4 of a second here. So this is, this rotation of this generator, in terms of the angle and also equated to time.